Okay, welcome everyone to this video. So today I'm going to show you a little bit about how to program in both assembly, MIPS assembly, and in C. Specifically, I'm going to look into how addresses work in assembly and how this corresponds to pointers in C. So we're going to write some program in assembly and then translate it into C. So let's take a look here at the prompt. So I got a Mac here with a UNIX prompt. It's basically a bash shell here. You can write commands, and you can see here ls that I have two files here, one assembly example file and one C file. So this is Emacs. You can use whatever editor you want, of course. And here we're going to write the C program, and then the assembly code will be written in Mars. So this tool for writing MIPS assembly and then execute it directly. So we want to declare some data, and then we're going to declare some code. And then the question is, how do you declare data in a assembly program? Well, we can use our MIPS reference sheet here to take a look at what we can do. So we know we got all the instructions here. It's not all MIPS instructions, but it's a selection, and we got the registers here. And if you go down a little bit here, you will see also something called assembly directives. So here you see, for example, that you declare the data section with .data. This is not an instruction. It just tells the assembler that we should have data here. And then you have something called code section, which says .text, which tells you that from this point and forward we will have code. And finally we will make use of something that is called .word here. So we basically will use this to declare a number of words in the data section. This is basically as declaring an array of predefined values. So let's go back to the Mars editor here, and then we write .data. Okay, so now we will have data here, and we'll write .text, and we'll have the code here. And we want to declare basically an array with some predefined values. So we need to give it a name. In assembly we do that by writing a label. So we call this LST for some list. And this will be the array. And then we write .word, which means that we will have word data that is coming here. So let's say 6, 3, 7, and 9. So now we declared 4 words in the data section. So what does that mean? Well, it basically states that this will be inserted into the memory from the beginning. And 4 words in a 32-bit processor means that we have 4 bytes in a row. That means 16 bytes in a row. So we can go here. If you see this sign here, we can go over to the view where we look at the actual assembly code and also the data segments. So the data that is in memory. And if you remember, we wrote 6, 3, 7, 9. And if we look at the memory here, we see that these values are actually 6, 3, 7, 9. They are defined here in the memory. So we see that the actual address of the where the data starts is 1001 0000. And this is up to the assembler to assign an address. So now let's see here. Let's say that we want to read some data from this array. First we need to get the address. So how do we do that? Let's go back to the MIPS sheet here, and then we see there's one pseudo instructions called load address, LA. So it's actually not really a instruction, it's more like a pseudo instruction that is then translated into several machine code instructions. So we'll see here that it will be equivalent to first doing a load upper immediate and then an ORI. So let's do that. So we write load address, and we want to get the value into, say, T0, and we want to get the address of this label LST. So let's say that we are running this program now. We go over here, and now we can see that this load address that we wrote in the source code is actually translated into the instruction LUI, and we see that we load up or immediate the upper 16 bits or the most significant 16 bits into a temporary register, and then we insert the rest, which will be zeros in this case. We will OR this. So these are instructions that are generated by the assembler. Okay, and when we run this with step 1, 2, we'll see that at T0 now we have the address 1001,000, which is this address over here. So we now have the address in T0. So now let's assume that we want to get this value 6 into T1. So then we need to do a load word. If you don't remember the syntax here for load word, you can of course always go to the MIPS sheet again. So you see here, this is load word here, and see load word, and then you have the syntax, the target address and the immediate value that we'll come back to, and the actual register that stores the address. So if we write here, we want to get the value into T1. We don't have any index right now, and then we say that the address is in T0. So we'll get the address from T0, add together whatever is in there, so it's 0, and that is the address. And then we will load the value from the memory and put the value into T1. So what do we expect to be in T1? Well, of course, since we were pointing to this first value here, 6, and we are loading this value, we expect that number 6 will be put into T1. So let's see if that works. We got the address here in T0, and we take another step here, and then we see that the value 6 is stored into T1. So I strongly recommend you now to pause the video, and then that you go back and do this yourself. So you open up Mars, and you basically type these things and run it and test it and make sure that you understand every step. Okay, so we have loaded a value into a register. Let's see what this means in C. So we'll write kind of the corresponding program now in C. So to make a simple C program, we first need to include some standard input and output so that we can print stuff. Standard io.h, like this. And then we need to have a main program. We write main, and then we, 0, which means that we have no errors. So we basically return code 0, just means that this program has no errors. Okay, and now we want to do the same thing. So we had in the assembly code this array here declared as LST. So let's do the same thing in C. So then we write an int LST, and it's an array equals, and we had 6, 3, 7, 9. So now we declare an array with a predefined value 6, 3, 7, 9. Okay, so to just test and run this program, we just want to see that it works. So let's write a hello world kind of start. So let's write printf hello, and we also add a dash or \n, so we got a new line, and like this. Okay, save, and then we see here that we have the ex.c file here. So we can compile this using gcc ex.c. If we do that and do ls again, we see that we get this a.out. So you can name it in a different way, but this is pretty simple. Then you to run it, you just write a.out. So this is that we are working on in the local directory, and then we're running like this, and then it prints out hello. And we can actually do like this, gcc and then ex.c and, which means that we'll first do the compilation and then run the program. And then we can easily just, you know, do arrow up and then like this and run it over and over again. Okay, so let's see here. So we have this print here, we can remove it now. And now what we would like to do is to take the first value out of the array. So let's first declare a pointer. So we write int star p equal lst. So we have now declared a pointer called p. It can be called anything. And a pointer is basically just a variable containing an address. And you could write like this as well. It's the same thing. So you can think that this is an integer pointer. It's called p. You can actually do like this as well. But the common practice is to put the star to the right. So lst, so what is happening here is that lst is actually just a pointer as well, pointing to the first element. So now we got p here. Okay, so let's say that we want to print out something here. Let's say that we want to print, and we're going to do many steps here. So let's call this number 1, and then we say address %x. This means that we will print out something in hexadecimal form, and then n. Okay, and then we say that we want to cast this into an unsigned integer, and then we give it p as an argument. So let's see what happened here. Well, we say that we want to print p, which is the pointer, and we cast it into an unsigned int. Let's see what happens when we run it. We get an address here, and this is in hexadecimal form. If we want to make it even clear that it is in hexadecimal form, we can write 0x in the beginning, and we get like this, right? So it looks familiar. So this is the address. It's the pointer. It's this pointer pointing to the first element. And you can see here that first time I run it, I got some value. The second time, and now I'm running it again, I get another thing. So it depends. The computer will just allocate some address and put these values into the memory. Okay, so I also did this unsigned int because the value that the hexadecimal output here, %x, wants is an unsigned int, not an integer that is signed, which is the default. Okay, so what if we want to print the actual value that the pointer points to? Printf, we still are at number 1 here, and then we say value, and we can just do a %d. So now we'll print it out using a decimal integer form. And then we do it like this. So with this star here, it means that we dereference the pointer. So instead of getting the value, as we got here, of the pointer, the address, we get the value that the pointer is pointing to. And since this pointer here points to the first element of this list, what we get back is value 6. So let's see what happens if we run this. We get value 6. Right, so we have the address, it's another address, but now we get value 6. Okay, so this is basically the same thing as we did in the assembly code. As you can see here, we loaded it. We didn't print really, we just looked at the register value. But we did exactly the same thing. We loaded the value. And let's say that this is the first part as well in this program. So let's go on with the second part then. So now we want to load the second element, this element. And we already got the address in T0. So what we can do now is to increment T0. So we increment it by 4. So, and this is number 2. So what happens here is that we know that these are bytes, but each word is actually 4 bytes. So that's why we have to change this pointer from pointing there to there, and then we had to add 4 because each word takes 4 bytes. So we add I, so add immediate with 4, and then let's do a load word again. So we write to T1. So we do like this, and we do basically the same thing again. So notice how we change the address here, added it by 4. And let's run this again. And we step forward. Okay, so we loaded the first value, it was number 6. And now we see that we increment the pointer, so T0 is 1001,000, and if we step one more step, we see that we have the next address, which is the next aligned 4 bytes address, and then we do a load word there, and then it changes T1 to value 3. Okay, so this means that we loaded this value, right? So we have loaded the second value now. Okay, let's do the same thing in C. So we have now, we want to increment the pointer. So we take the next element. And then it's very tempting, of course, to do like this. So we have the pointer and pointer plus 4. But this will not be correct, because in C, you do not reason about bytes in memory, but rather values. And since this is an int declared as an int array, if we increment by 4, it will jump 4 elements forward. So what we should do is just to increment by 1, and then the compiler will know that this is actually an integer, so it will move forward by 4 if it's a 32 bits processor running on it. Okay, so let's do that again, and now we can just copy these 2 lines and put it there. I mean, usually you don't want to copy code, but here we'll do that just for an example. So we'll print P again and print the value. And let's clear here, clear, and run it again. Okay, so what we can see here is that first we got this address, we got value 6, which is this one, and then we incremented the address, so we did this P plus 1, but then now we have plus 4. Now when we load the value from this address, we get value 3. And this is again using this dereferencing notation, so we get this value here. Okay? Next, let's see if we can change the value in memory. So we can, for example, increment the actual value. So we know that we got this value 3 here into T1. What if we add now, and we add a value 100 to T1? So the T1 is now the value that we got from memory. It should be value 3. And we add 100. So now we should do a store word, T1. And we got a 0 and parenthesis T0. So let's see here, what does it say? Well, we have a T1, and what we do now, it's basically the same thing as load word, but instead we do a store word. So we take the value inside T1 and put it into the address where T0 is. And since we know that we were pointing to this one, we should change this value, number 3 here. So let's do that and run it. So again, we just go through here, we load the first part. We now have loaded the value 3 into T1. We increment T1 with 100, so 67 because it's in hex. You can change here to see that it's 103. No, it's 103. And then now we want to change this value in memory. That's why we do a store word. So we do it once more, and then we see that we change this value into 67 hexadecimal or 103 in decimal form. Okay, so now we have stored a value, and this is part number 3. Let's do that in C. Okay, so again, now we are going to store a value. So then we write instead star P on the left hand side. So now we are dereferencing where we're going to write. So we look here, we change the pointer. Now we're going to change the value that the pointer is pointing to, and we're going to again grab the value that's there right now. We know that this will be 3 here, plus 100. Okay, and then we want to print this out. So copy that line, and then we have here number 3. So we want to print out this value, and we print out the value that is stored on this position. Let's run this, and we see that we have here value 103. So this is the value that is now stored in this place in memory, which is exactly the same thing as we did here when we used store word. So as you can see here, an address, a pointer is just a variable with an address. That's all we have. Okay, so finally we want to load again, do a load word, but now I want to do a load word where I do use the index. So I'll do $T1, comma 8, and then $T0. So here we see that, and then we say that this is number 4. So we see here that we have T1, and now we're using this index. So this means that we jump forward by 2 words. So remember that T0 here pointed to this one, and now this address plus 8 will be the actual address that is used for loading. So that will be plus 8 will be plus 4 plus 8. So we'll read out the value 9 here. Let's do that. We go through the other steps here, and now we store the value, and now we should read this value 9 into register T1. So let's do that, and here we run it, and now we see that we get value 9 into register T1. So it was adding together the address in this variable plus 8, and that's why we went forward 2 words and grabbed this value. Okay, so let's do that in C as well as the final thing. So now we want to take the value and just print it out. So we can copy this line again, the printf, and here got number 4. So in this case we just printed it, we grabbed the value that the pointer was pointing to, but now we want to index 2 steps forward in the array. So what we can do then is just to do like this, plus 2. So now we're moving the pointer 2 steps. Again, do not do plus 8 because we are in C, and then the compiler figures out by itself how many bytes there is in one word. So we will do plus 2, and then so it basically increments the pointer and then dereferencing it so it gets the value where the pointer is pointing to. So let's run this program, and as you can see we get the value 9. So we were reading this part. Okay, so this was what I wanted to say about assembly and C programming, and I hope that this will clarify a little bit about addresses and pointers, because these are really the same thing. And a pointer is basically just a variable with an address, and you can use this address to grab the value that the pointer is pointing to. Okay, thank you for listening.